Hello, everyone. My name is Renato, and today I'd like to present a paper entitled Distribution Testing with a Confused Collector. And this is joint work with Nathan Harms, who is currently a postdoc at EPFL. So our work is about distribution testing. So let me first give you a picture of the standard distribution testing task. So the way this picture goes is that we have some unknown distribution D, and we would like to test some property about this distribution. For example, is it a uniform distribution, or is it equal to some reference distribution that we care about, and so on. And the way we're going to do this is, well, this distribution is over some domain, which here I'm representing by this grid, and we're going to draw samples from it. And these samples are represented here by these points on the picture. Then we feed these samples to some sort of algorithm, and that algorithm will use the sample data to make some sort of decision, like is the uniform distribution, or it's far from being uniform, and so on. And the question that we are interested in this model, as hinted by the confused collector part of the title, is what happens when we have mislabeled data? Can we still make any kind of reliable decision about D if the data fed to our algorithm has the potential to be mislabeled? And before I dive into this in more detail, let me motivate this question by giving you some informal but hopefully illustrative examples. So the first example is, suppose that in a scientific study, we're researching the distribution of woodland flora. However, the research assistant collecting the data is not really able to tell apart some of the species that look too similar. So there are going to be some labeling mistakes there. Another example, maybe our data has been labeled by a machine learning classifier. Or perhaps our sample points have been truncated due to rounding or hashed to save space, thereby introducing collisions in my labels. And finally, maybe I'm studying the distribution of fossils over time. However, fossils from years X and Y in the rock can only be distinguished if there's some random geological event that occurs between them and leaves a trace on the rock that I can use to tell them apart. So in all these cases, there is the potential for the data, the labels in my sample to be incorrect. So here, if I go back to my picture that I was describing before, what's going to happen is that maybe I have regions of my domain, like this green region or this red region, where my data collector is not able to distinguish these points. So really the way that the data going to my algorithm looks like is more like this. Everything here just looks like a green point, and everything here just looks like a red point, and they're not further distinguished. Now, can we even make any reliable decisions about D at all in such a case? And before I tell you our answer to this question, let me briefly mention some related work. So the first one by Fotakis, Calavasis, Contones, and Zamos dealt with statistical learning with what they call coarse labels, which is in spirit similar to the motivation that we care about. However, here, to perform statistical learning, in their model, they assume that for each element that is sampled, a fresh coarsening, which is a partition of the domain, is drawn at random, and then the coarsening to which the sample element belongs is given explicitly to the algorithm. Okay, and then they require that the distribution over these coarsenings or these partitions is required to be what they call information preserving, which is some sort of statistical or information theoretic requirements. And the difference to our motivation is that here a fresh coarsening is drawn for each sample element, but here for the question that we're interested in, we assume that we only have one collector, not many collectors. And if our collector is unable to distinguish some elements, then they're always going to make that mistake no matter how many samples I draw. And also, we're not going to want to have explicit access to this coarsening. We will need to discover the mistakes by ourselves as we perform the testing task. Second, in recent work by Goldreich and Ron, they introduced the huge object model for distribution testing. And in this model, the objects are basically too large for us to know the sample with no cost. So basically, the algorithm needs to perform queries in order to learn the label of each of the sample elements. And it can perform as many queries as it wants to either learn a lot about the objects or just learn a little bit, depending on the testing task. So this is kind of similar because there's imperfect information about the labels. However, a crucial difference is that here, the algorithms can learn to as good a precision level as they want, as long as they issue queries. Whereas for us, if the collector is making some mistakes, then these are just mistakes that are always there, and we can't really learn beyond that. There's also similar or related in spirit work by Cannon and Wimmer on identity testing when the input distribution is promised to be permutation of the original labels of the distribution. So here, perhaps the collector has scrambled the labels by mistake, and then they try to fix them back, but they're not sure whether they succeeded or not. So they can use this algorithm to test whether they recovered the original distribution or not. And I invite you to look at the paper for some more connections and conceptual similarities with other work. So now for our work, how do we plan to deal with this motivating question that we have? Well, the first observation is that naively, if we allow worst case mislabelings, then testing is just impossible. Because even in the simple picture, distinguishing between a singleton distribution on one of these green points and a singleton distribution on another of the green points that is somewhere else in this region is completely impossible because the points look the same. Okay, so there's nothing we can do. And our contributions then come in two parts. In part one, we essentially overcome this challenge that testing is just impossible and show that we can test even under worst case mislabelings as long as we define our model carefully enough. And we consider this model, the problem statement, to be one of the main contributions of the paper. And then in part two, we go beyond these worst case results and show that for certain random mislabelings, we can do even better by exploiting the structure of the problem. Okay, so let me give you the setting that we're going to be working in a little bit more concretely. The first assumption, as I've hinted at, is that our domain is going to be a metric space. So here my domain X captures the grid in this picture, and then dist is some notion of distance between the points. For example, Euclidean distance or any kind of LP distance. And the reason why this is a reasonable modeling choice is because we essentially expect intuitively that the labeling mistakes are not completely arbitrary. They have something to do with the semantic content of my domain. Okay, so points that are close together in the metric space perhaps are more likely in some sense to be mistaken to be the same. And we're going to actually capture this notion with our notion of distance with respect to which we will test the property of the distribution. Usually in distribution testing, we test against the total variation distance. But here, to capture this metric space in a stronger way, we're going to test with respect to the earth mover distance. And I have the formula here for the earth mover distance, but the intuitive idea is that the earth mover distance, the EMD between mu and nu, captures how much mass do we need to move to transform mu into nu, and how far does the mass have to travel. So I'm going to choose a coupling pi, and then for that coupling, for each points x and y in my domain, I multiply the mass moving from x to y by the distance that the mass has to travel. And the intuition for why the EMD will be helpful for us is because if only the similar or close together elements are confused with each other, it essentially means that the mass is only traveling a little bit. So the EMD between the distributions is not changed by too much. So perhaps I can still test even after these mistakes have been introduced. That's the idea. And how exactly am I going to model the labeling mistakes? So we're going to assume that the collector holds an unknown clustering of my domain, which is a partition gamma 1 here to gamma k. And each cluster gamma I contains a representative point in the space, denoted by rep I. So here the green cluster is the cluster gamma 1 with rep 1 point here, and gamma 2 is the red one with rep 2 here. And now I can describe the access to the input that we're going to assume. So there are going to be two types of access to the input. The first one is samples, namely cluster samples. And what this means is that first, a point X is drawn from the underlying distribution D. But then if it belongs to the ith cluster, gamma I, then the only thing the algorithm will see is not X itself, but its representative rep I. Okay, so this is the mislabeled data. And what else can the algorithm learn about the input? Well, we can learn something about the labeling function of the collector. And the way this works is that we have label query access of the following form. The algorithm can pick any point X that it likes and ask the collector, what do you think is the label of X? And the collector will say, for example, it's rep I, okay, for the same I as I described here. So our goal is to test the property of the distribution D that we care about while minimizing the number of samples and the number of queries, hopefully accomplishing sublinear in both cases. Okay, so how are we going to do for this part one, testing under worst case clusterings? And for now, the problem is still infeasible because if I allow arbitrary clusterings, then I could have a cluster that contains points very, very far apart in my domain. And then there's nothing I can do because, again, the same kind of counterexample as before is going to be bad even under EMD. However, if my clustering is low diameter, then that's the intuition that I introduced before. Low diameter clusterings are helpful because only points that are close together have been confused together. The problem is we don't want to require the collector to promise that the clustering is low diameter, because the collector may be unable to fulfill this promise, and they may not be correct about their knowledge of the domain. They just make some labeling mistakes and there's nothing they can do about it. So what is our approach instead? We're going to require a much weaker promise from the collector, something that is more reasonable to expect to be fulfilled. And then we are going to test the clustering ourselves. So we are going to detect either this clustering is suitable for our job and we're able to test the property of D, or the clustering is unsuitable and we will just say that in the output. We are not going to make a wrong decision, basically. And this is inspired by the testable learning framework of Rubenfeld and Vasilian. Okay, so now I can formally describe our task. Recall that the domain is a metric space X dist. So here, think of the domain as, for example, the hypergrid in D dimensions or the continuous unicube under any LP metric. And first, we fix a universe U of the so-called reasonable clusterings, for example, the convex connected ones. And this is the only promise that we require from the collector, okay? Then within this universe, we pick a set G of the good clusterings. So these are the ones that are even more nicely behaved and easier and better to work with. For example, the axis-aligned boxes that are low diameter. Low diameter, recall, was something that was very helpful for our testing task. And this is the assumption that we will not require as a promise, we will just test ourselves. And I won't go into too much detail about what low diameter means, but you can think of it as diameter being smaller than epsilon, where epsilon is an error parameter. And this is something that we will just test ourselves. So now a tester for the property P of distributions has to satisfy the following criteria. First of all, if the input distribution is in fact in the property P, then it has to, with high probability, either accept or cluster reject. And I'll tell you more about that in a second. On the other hand, if the input distribution is epsilon far from the property P, then it has to either reject or again cluster reject. So now why can't it just always cluster reject and be a valid tester? Because of the third criterion, which is if the clustering is in fact a good one, that is, it comes from a set G, then the algorithm must not output cluster reject. So it has to actually say accept or reject. That is, it has to say something informative about P. Okay? So if you combine these three criteria, you see that you get something that is informative as often as possible, essentially. But on the other hand, it is not fooled by the labeling mistakes. It just decides that it cannot give a reliable answer. So let me briefly mention some of the results that we have for this part one. We basically give a general lemma that can combine different choices for the ideas that I've introduced so far, like the domain, the universe of clusterings, the good clusterings, and the property of distribution that we care about. And then combining those different ingredients, we obtain testers for different settings. In terms of techniques, we essentially combine various ideas, including prior work on testing with respect to the Earth mover distance by Doba, and Rubenfeld, as well as specific techniques for testing the classes of clusterings that we care about. For example, for some of them, we use convex optimization techniques. And there are additional arguments that I invite you to look at the paper for. We give testers for properties of uniformity, identity, and equivalence or closeness of distributions in a variety of the settings that I've just mentioned. And here, let me just tell you a few examples for equivalence testing that will tell you the flavor of the results that we give. So here in this first example, my domain is the discrete hypergrid in D dimensions, where D is a constant. Both my universe of clusterings and my good clusterings are both the connected and convex clusterings. So this is the clusterings where every cluster is convex and is also connected in the hypergrid. And my sample complexity is just some function of 1 over epsilon, some poly 1 over epsilon. And this is going to be the case for every example. And the query complexity, well, there's some dependence on epsilon. And most importantly, the dependence on the domain size is sublinear when D is a constant. So now if we move to the second application, where we give a result for 2 dimensions, so the special case, what happens is that if we move to a more restricted set of good clusterings, only the axis-aligned boxes, so we're only required to we're only required to not cluster reject, but rather process the clusterings that are axis-aligned boxes, then our query complexity improves to logarithmic in n. So this is an exponential improvement when we restrict the set of good clusterings. And finally, for a slightly different domain type, when the domain is the continuous unicube, again in constant D dimensions, and now my universe being, again, the convex clusterings, where each cluster contains a delta ball. and with the same set G of axis-aligned boxes as the good clusterings, then we have query complexity that has some 1 over epsilon again, and then polylog and 1 over delta dependence. And you can think of 1 over delta as some sort of notion of the length of the domain, more or less. So polylog 1 over delta is quite efficient. Okay, and then I invite you to look at the paper for more details and some of the techniques that we use. Let me move on to part 2. As I mentioned before, what happens if instead of requiring to handle worst case clusterings, the clustering actually comes from some underlying, from some distribution, so it is drawn at random. Why is this interesting to study? Well, you can think of the clustering as coming from some sort of environmental randomness that is uncorrelated to the distribution that I'm testing. For example, maybe the fossil scenario that I introduced in the opening. And there are also some applications related to distribution-free property testing tasks. And I invite you to look at the paper for more details on that. So we would like to understand, can we do anything better when we have these random clusterings? Let me fix as the domain, the discrete line from 1 to n, and assume that my clusters are contiguous. Okay, so this is the problem that we're going to be studying to start attacking this question. Now, what is the distribution of my random clusterings? It proceeds as follows. There's a resolution parameter rho given between 0 and 1. Now, for the way that I draw a clustering is for each pair of adjacent elements, I independently decide to separate them into different clusters with probability rho. So if rho is equal to 1, I have perfect distinction. Each cluster is just a singleton. If rho is 0, I just have one cluster that includes everything and everything in between. Okay, so our goal in this model now for this problem is to study uniformity testing. And as a benchmark from the worst case results, because these are a special case actually of the axis-aligned boxes. So as a benchmark, we do have EMD tester using roughly 1 over epsilon squared samples and the same order of queries. Okay, so we want to give a stronger result than this. And in what way are we going to give a stronger result? Well, in 2 ways. First of all, we're going to give a tester under the stronger total variation distance. So this is much stronger than EMD. And second, our tester is going to use 0 queries. It will only use samples. And this is important not only in the quantitative sense, that is much better query complexity, 0, but also qualitatively, there might be motivations or applications where we do not have access to these label queries. And the sample complexity of this tester is n square root n over rho to the 3/2 times epsilon squared. So basically, this is comparable, is the same as the standard complexity of uniformity testing, except that we pay a cost that comes from the resolution parameter. And the main technical idea is to extend the collision-based tester, the classic collision-based tester. The way this works in a little bit of math is that we have a random matrix phi, Boolean matrix, that encodes the clustering by assigning 1 to phi ij when I and j are clustered together. And we have a random vector t, such that ti is number of times I appear in the sample. Then the test statistic for the collision-based tester is essentially very closely related to the random quadratic form between t and phi. So our analysis needs to give a concentration result for this random quadratic form. And we do this by first studying the minimum eigenvalue of the expected matrix phi, and then also techniques to control the variance. Let me briefly mention that if we allow queries, it is actually possible to do better with the dependence on rho. And perhaps to stimulate your curiosity, we informally call the tester that accomplishes this the ignorance is bliss tester. This name, I believe, does not appear in the paper, but if you're curious why this name made sense, you can look at the paper. So in summary, we give a model for distribution testing with mislabeled data. By combining samples, label queries, and the Earth mover distance, we can withstand even worst case clusterings. And the key step here is that the algorithm detects the unsuitable clusterings by itself. And finally, if we have random clusterings instead of worst case, then stronger results are possible, for example, uniformity testing under TV distance. Let me briefly mention some directions for future work or open questions. So one is, how can we combine the expertise of multiple collectors? If we have multiple collectors available, can we automatically detect and efficiently combine their expertise for a better decision-making? Also testing other properties of distributions, for example, monotonicity or k-histograms, and these are not preserved by clustering. Or third, perhaps, are there other properties that also admit testers under the stronger total variation distance? And finally, are there other natural types of random clusterings that are worth studying? And if so, do they also admit zero query testers? So I'll leave you with these questions, and for now, thank you very much.